Good evening, Grant Lewis. Welcome to Late Night in the Midlands. How are you?
I'm good, thank you. How are you?
I am doing just fine, and I want to welcome you to the show, and we are live. So thank you for being here.
No problem.
All right, great. Well, I thought maybe we'd start with a little bit of background and where your interest has led you in this field of astrophysics.
A bit of background. Okay, so I'm actually a professor of astrophysics at the University of Sydney, and my area of research is focused on mainly cosmology, studying the large-scale universe, gravitational lensing, and an area known as galactic cannibalism when one galaxy eats another galaxy. So those are the key areas I work in, but I've also got a strong interest in lots of physics, actually, especially things like special and general theories of relativity.
I see. And what's your thoughts? I don't know if you've seen it, but I've seen an article where there's these two stars kind of merging as one. Do you know what I'm talking about? And what's your thoughts on it?
I'm not sure exactly which one. There's a lot of merging stars out there. There's especially very dense stars, neutron stars. They're the ones that they spiral together and they sort of eventually collide. So we see stellar mergers quite regularly. But do you remember what the key point of the one you saw was?
No, they said that it was a binary star system and that the two stars, their centers, looked as though they were combining to each other and was going to become one big star, they said, and then, of course, it would, turn into black holes because it would probably collapse on itself. Yeah. But I think they said it was the closest. I can't remember offhand. I think it was they said it was a very close star system.
Okay.
And so they got a good look at it, and that's all I know really about it right now. So that's why I thought I'd ask you.
Yeah. There's a lot of. In fact, most stars in the universe appear to be in binary systems, but most of those stars are well separated. So one star doesn't really influence the other star, other than in its orbit. But we do see some stars that are close enough that effectively they're touching, and there's mass going from one to the other. And especially when you get these really dense little stars, these neutron stars, that's when their orbits basically lose energy very quickly, and then they collide together, and you get a violent collision, possibly black hole formation when that happens.
I see. So then, is there any evidence of anything like that? Not that two stars combined here in our solar system, but I might as well get it right off the table now because people will want to ask. Is there any evidence of a second star, a dark star, or anything like that out in or around our solar system?
You mean as in orbiting our sun?
Well, it could be. I mean, anything like that. I mean, so I hear that, people say, well, there's a dark sun out there somewhere in our solar system that, our sun has to have a companion somewhere.
Not that we can see. I mean, the thing that's happened in the last sort of 20, 30 years, which has changed astronomy, is that people have surveyed the sky to great depths and at many wavelengths. And if there was anything remotely like another star anywhere near our solar system, we would have seen it, and we would have also detected its gravitational influences. So our sun does appear to be just a lone star. There doesn't appear to be another star anywhere remotely close to it. Wow. I mean, the smallest, dimmest stars we know are red dwarfs, but we would easily see a red dwarf star anywhere close to us.
We would. So, because I have people who tell me that, well, it's not coming across the solar system. It's coming from below, or it's coming, they tell me that I wouldn't be able to see it until, it was too late.
No. So astronomers love those areas above and below the solar system, right? Because, the planets are out of the way. So we look in those areas all the time, and there's not another star hidden there.
All right. And if there was something, this is something that I've brought up before with all the amateur astronomers and there's always somebody out there who would love to be that whistleblower. And so that's why it's kind of hard, for me. I've always been on the middle of the fence with it. Like, I don't know. Maybe there is something out there, but, I know there's a lot of baloney about it. So. I thought I'd bring it up.
Yeah.
Yeah, so we don't have nothing. Oh, what about this asteroid that's supposed to be coming close to the planet on Halloween now? Do you know anything about that?
Oh, there's probably a lot of them that's come close to the Earth's orbit around this time. I mean, there's a lot of bits of rock in the solar system. I mean, again, from looking at the sky, we see that the solar system is filled with rocks of various sizes, and lots of them come across the Earth's orbit. But for all the ones that we've detected, and we're now trying to get down to the smaller ones. We know that the chances of any of the bigger ones hitting the Earth are next to nothing for. I'm not sure how long the time frame for it, but it's many decades into the future. We can be pretty sure that we're not going to be hit by anything reasonably big. There are still lots of relatively small rocks, of the hundreds of feet or smaller size, which will hit the atmosphere. These things hit quite regularly. So we will have continuous bombardment of meteors and meteorites, etc. But none of the big stuff is coming close to us.
Okay, and so then it was probably just a freak thing, I guess, with Russia then, because I found it kind of strange that we had an asteroid, as you know, that day or around that time that was passing close to Earth, and NASA had said that we had nothing to worry about, which so a lot of us didn't. But that comet, I think, came because of it, and hit Russia. But they say no, it wasn't connected. I mean, could it have been?
Well, they will be very different sizes. I mean, I know the rock that exploded above Russia looked very spectacular, and explosion-wise, it was a big explosion, but very high up in the atmosphere. But the actual rock that did that was probably quite small, of the tens of feet size. The rock that NASA would have been monitoring would have been something much larger, probably the hundreds of feet sort of diameter. Those ones are ones which could do substantial damage if they hit the Earth. Could they have been associated? Possibly. I mean, the rocks are not just often lone rocks. You get one or two of them traveling together, and this might have been a small piece following the big piece. But there are lots of astronomers at the moment now who are looking at that dash cam footage, looking at the entry trajectory of the rock, and trying to trace the orbit back to see where that rock came from. But we probably get hit by rocks, of order that's tens of feet quite regularly. It's just that most of them will be over the ocean, it's only now we get into the time where everybody has a camera on them, right? So they can photograph these things. So they're not that rare.
A little rock, as you called it, like that, and the havoc it caused in Russia, I couldn't imagine something big. I mean, what would it take to affect the entire globe? I mean, I hear that, like rocks like what hit Russia, it's kind of isolated. And so I guess whatever they think took out the dinosaurs had to have been really, really big, right?
Yes, so that's when you're getting up to kilometer size. And there are, we know there are chunks of rock kilometer size and bigger in the solar system. So the big thing that's happened about the Russian one is that it exploded in the atmosphere. So it was a big explosion, but it was high up. The dangerous ones are the rocks that can get down low into the atmosphere and explode close to or on the ground, and they're the ones that can have damage over a very, very large area. But those are the ones that we're trying to track. That's why there's a whole range of telescopes around the Earth now which are being set up to monitor and search for these rocks of 100 feet plus and try to monitor them and work out their orbits for the future.
I see, and I'm sure they try to monitor other planets that get hit. I know a long time ago one was going for Jupiter, but Jupiter, I mean, we didn't see much except for a flash. I guess it'd be nice, as long as it's not this planet, to watch something like that.
But yeah, so for Jupiter, it was hit by Schumacher-Levy 9 back in, I think it was 91. It was quite a while ago now. And you have to remember that Jupiter is a very different planet to the Earth, right? It's gas and then liquid, and then maybe in the middle there's some rock. So there's no surface to hit. So the thing when it actually goes through the atmosphere and explodes in the atmosphere, similar to what happened above Russia, the energy gets dissipated into the gas. And so there were scars on the clouds of Jupiter. I mean, and those scars were much bigger than the Earth. But eventually the clouds basically mixed it all away and it disappeared. But, there was a very large amount of energy was deposited into Jupiter's atmosphere from that. Yes, we don't want it to happen to the Earth.
Yeah. All right. So now I've had guests come on and kind of I've had a couple lately who disagree on the aspect of gravity. And I've had some tell me gravity pulls, others say it pushes. And I thought maybe you could explain gravity just a little bit for us and why we do not detect the movement of the planet, etc. Because there's also, in another part of this, there's those who are trying to convince everybody that the world is flat. And still, I believe it or not. And so I thought maybe you can get in a little bit about gravity and why we don't feel the movement of the planet.
Okay, so where to begin? I think the best place to start is with Isaac Newton, right? So this is now back in the 1600s. And what Isaac Newton did for us is he gave us a mathematical description of how gravity works. So high school children learn this now. They write down Newton's laws of motion, Newton's laws of gravity, etc. And what Newton told us is that if you have massive objects, then the amount of gravitational pull you get depends upon how much mass you have there. And it depends also on the distance apart, or the square of the distance apart. And it's an exceedingly powerful mathematical law. So so Newton was able to calculate how fast an apple falls, and using the same equation could calculate how long it takes the moon to go around the Earth. And it's the same mathematical framework we use today if we want to put a rocket into space, or the New Horizons flying to Pluto. They used Newton's law of gravity. Now, what Newton's law of gravity doesn't have in there is an explanation for what gravity is, right? It's just a law that tells you that this is how much force you get. And to describe gravity in the modern context, what we use is Einstein's general theory of relativity. So this theory is 100 years old this year, and Einstein basically wrote down his famous set of equations, which was a new description of gravity. And that sort of encompasses already what Newton had told us, plus there's extra information. And one of those extra things that's in there is that gravity is related to space and time. So you've got this concept of space-time, and that gravity is the distortion of space-time. So you have a massive object, it distorts space-time, and that distortion is the gravity that we feel. So that particular theory of gravity is exceptionally powerful in that it describes things very, very accurately. It describes the motions of the planets very, very well. So you've got Mercury's orbit, which was always found to be slightly discrepant with Newton's description. But when you use Einstein's general theory of relativity, you actually get the orbit extremely accurately. So that's what we now know as gravity. We talk about gravity in terms of Einstein's general theory. Now we know that that general theory of relativity can't be complete because there's a tension in modern science, and that tension is between Einstein's description of gravity, which talks about the universe on the large scale, and quantum mechanics, which talks about the universe on the small scale. And when we want to try and use those two descriptions of the universe together, we find that they don't really work together. And this is why people feel that there's got to be a next step up in terms of of how we understand the universe, which combines quantum mechanics and gravity together into this one framework. So we have a really good description of gravity. We know it's not 100% correct, and people are working on trying to get this unified picture. So the question you have about why people don't feel the motion of the planets is, I think you have to turn the question around and ask yourself why you would expect to feel the motion of the planets. So if you are in your car and you're trundling along the highway at, trying to remember, it's 55 miles an hour is your typical speed in the US?
Yes, sir.
Yeah. You don't feel the motion, right? I mean, you feel the shaking of the car and you can hear the wind blowing over the car, etc. But your body doesn't sense that motion. In fact, your body can't sense motion. So if I took your car and I put it into space, and so that you're not rumbling along the road and there's no wind blowing across the car, and I give you a big push and then off you go sailing through space, you would not feel that motion. We don't feel motion. What our body feels is acceleration. Our body is an acceleration detector. So when you hit the gas, you feel that acceleration because the car pushes against you. And when you slam on the brake, you feel the deceleration. But actual motion, you don't feel. And this is something that we've known for a long time. This is what Galilean relativity, this was what Galileo worked out in the 1500s, that you don't feel motion. So you wouldn't expect to feel the motion of the Earth unless the motion of the Earth radically changed, i.e. there would be a force acting on it, and then you would feel the acceleration.
Ah, okay, I see. Okay, it makes a lot of sense, and they've also brought up the fact that they say, well, if the Earth is spinning as fast as they claim it is, I'm just going to throw a few of these at you. Then how come the clouds aren't zipping by and so they bring up things like that. But I've had people who, and I'm sure you've heard of this theory this conspiracy theory really is that the Earth is flat. So what would you say? You probably don't even want to entertain it, but what would you say? No. What would you say to those who claim the Earth is flat? I've actually never done it. Art Bell's got me beat on that one. He did a show on it. I have not, and I may be a party pooper, but I don't see any reason to.
So, I mean, I don't want to sound insulting to people, but I think with just a teeny bit of science, it's easy to see that the Earth is not flat. I mean, the ancient Egyptians worked out that the Earth is a sphere, and I don't think that everyone's been deluding themselves for several thousand years. So the issue with the clouds is a good one, because yes, we would feel the motion of the Earth if the atmosphere was static and locked in with respect to the universe and the Earth was spinning underneath it, but it's not. The atmosphere spins as well as the Earth. So and that's what you'd expect to happen. If you could imagine that we had a still Earth and a still atmosphere, and we start to spin up the Earth, what's going to happen is that friction between the Earth and the atmosphere is going to start the atmosphere moving, and it's going to keep having that action until the atmosphere is moving basically with the Earth. And so that's what we have now. The atmosphere moves on whole with the Earth, but we also detect the rotational effects of the Earth in something known as the Coriolis force. So this is one of these things that you get because you have forces acting on a sphere rather than on a flat plane, which causes things basically to spin over the surface of the Earth. And as we know, that Mexico is just about to be hit by a hurricane.
Yeah, it might even be on them right now.
Yes, and that hurricane is huge, and it's spinning, and that spin that it's picked up is because of the rotation of the Earth. I mean, that's what spins up hurricanes, is that the winds blow, and they go north and south, and as they move north and south, the relative motion of the Earth underneath is different, and that spins them up. So the powers of the hurricanes are given to them by the actual spin of the Earth at some level.
So if the Earth sat still, then we wouldn't have really any kind of weather movement to speak of.
You would still have some, because there's a coupled effect. one of the effects you have is heating from the sun, which heats at the equator, and so winds would flow north. So hot air would rise, it would go to the north and then come back down to the south. So you would have a north-south wind. But we've got that going on a rotating Earth. And so you then have winds trying to go to the north, but then spinning off to the side due to the rotation. So, yeah, we would still have weather, but it would be quite different to the weather we have now.
Okay, I see. Now, somebody had brought up a really good question in the chat room, and that is, when we go through meteor showers and all the stuff that's going on in space, how come our satellites, we've got so many satellites out there, how do they survive? How are we still using our cell phones and stuff?
So meteor showers are kind of interesting because many meteor showers are remnants of comets that have traveled through the inner solar system. So a comet is a dirty snowball. All this stuff comes off the comet. We see these great tails, and these tails actually linger around for a long time. And when the Earth goes through those tails, we get a meteor shower. The meteors that we see in a meteor shower are not rocks of 1, 10, or 50 feet across. They're actually grains of sand. Okay? So they're actually really tiny little bits that fall in and flare up and then disappear.
But we are told that grain of sand, if we were in space and it hit us, it would go right through us, wouldn't it?
Absolutely. But you have to remember that the relative densities of these grains of sand is very low. Like if you go out and look at a meteor shower, you can be sitting there for an hour and you might see a handful of meteors. Now and again, if you're lucky enough to go out and encounter a meteor shower just after the comet has come by and refreshed the tail, then the sky might light up, right? You might have lots and lots of debris there. If it's a typical one, there's only, scatterings of bits of sand. So yes, there would be very dangerous to you if you're up there in a space station, in a spacesuit and one hit you. But you have to remember that the guys that design the satellites, they know what the environment is going to be like, and satellites are somewhat hardened to the environment of space. So they are somewhat protected, but they do encounter collisions. Now, one thing I do know is that the other people that care about this are insurance companies. Insurance companies want to know what's the things that are going to knock out satellites. And satellites actually, when you go through the numbers with regards to meteor showers, the chances of them being knocked out are relatively small. It's not that it doesn't happen, but it's quite rare. The big risk to satellites are not meteor showers, but actually solar storms. So solar storms are different. They don't hit, they don't hit with like little bits of rock, but they hit with particles, they hit with protons, etc. from the sun. And that actually can knock out swathes of satellites and also knock out power systems on the Earth. So, yeah, it's not meteor showers you should be scared of, it's solar storms.
I see. Okay, so it's kind of like on a small scale, just like we're protected in our car from our windshield. So it's made for little rocks to bounce up from the car in front of us and hit. And sometimes, every now and then, your window will crack from it. So satellites, I guess, basically the same way then.
Absolutely, yes. In fact, there's a well-known picture. It's very easy to find on the web of the window of the space shuttle with a gouge out of it, which they think was caused by a flake of paint hitting, and that would have hit at like 20 kilometers per second and gouged out a chunk out of the windshield of the space shuttle. And again, the guys that designed the space shuttle made sure they had pretty thick glass on the windows because they knew those kind of things were coming.
Wow. Hey, you know what, boy, that would be a catastrophe if the windshield got taken out, wouldn't it?
Absolutely. But as I said, the people that design space stations and spacecraft know the environment and know that, like when you design a car, right? You know what it has to put up with, and you consider what worst case scenario is going to be like, and you try and over-engineer to ensure that you keep your astronauts safe.
Okay. So now another question here: if someone traveled at the speed of light, that person would return to Earth and be much younger than those he or she left behind. I think they're talking time travel here. What do you think about that? I mean, is that how it works? I mean, if we go so fast, would we? Yeah.
Absolutely. So basically, that's a very famous. That's one of the things we use to teach relativity to our students, actually. So it's called the twin paradox, even though it's not really a paradox. That if you have a pair of twins and you send one off into space, and they travel at very high speed, close to the speed of light. You can't travel at the speed of light, but close to the speed of light, and then come back, then they will be considerably younger than the people that they left behind on the Earth. And that's something that we can test in the lab. In fact, we test it every day with experiments looking at the atmosphere. So there are collisions in the upper atmosphere where some of the solar wind and high energy particles hit the atmosphere. They create a heavy version of the electron called a muon, and that muon has a lifetime. And if you've made one in the lab, its lifetime is very short. It's a millionth of a second or some number like that. But when you create them in these collisions in the atmosphere, they actually are traveling close to the speed of light, and they appear to live longer because of this effect known as time dilation, that the time for one person is not the same as the time for somebody else. So these are things that we can actually do experiments on and do directly, and time is a bendy, rubbery concept. It's not a rigid thing like Newton proposed it to be, where everybody's clock would tick the same. So, yeah.
So time travel, it actually is possible, and that's going forward and back, or just one way?
Well, there's a couple of bits here. So time travel into the future, of course, is straightforward. We're all traveling into the future at some level at 1 second per second. Through Einstein's work, you find that everybody's clock ticks at a different rate. So you can get somebody to go off, spend time somewhere else, and come back, and a different amount of time will have passed for the two of you. So for one, they will have traveled into the future of the other. So you can either go off and fly through the universe at high speed, or you can go and sit somewhere in very strong gravity, so gravity affects the way clocks tick as well, and come back, and you will have effectively traveled into the future. Amazing. Time travel into the past is a harder one because, let's put it this way. So if you work with the mathematics of general relativity, time travel in terms of those mathematics is possible. Nothing in there says you cannot travel backwards in time. You could bend space and time sufficiently such that you could travel backwards in time. The question we have is there any way of manipulating space and time such you could ever build a practical time machine? So it's allowed by the mathematics at the moment, but we don't know if it's something that's physically allowable. So to give you an example, there's a famous universe proposed way back in the 1950s, and it was proposed by Kurt Gödel, who was a famous mathematician at Princeton at the time. And he showed that if you could get the entire universe to spin, then inside that spinning universe, one of the natural things that would happen is you could travel into the past. So that's good. It's all part of the mathematics, but can we spin the universe? Well, that sounds something that's physically quite impractical to do. So it's allowed by the mathematics, but we don't know if we could ever really build a time machine yet.
I see. Now, then I would wonder about, even if we could do it, the problems that would arise from something like that. I mean, if it became common like the automobile, well, then there'd have to be a system in place, because can you imagine what people would go back and do? And I just wonder what kind of implications that would have. Would we go back and just see the past, or would we actually interact with it? Now, that would be, I guess, the big question.
Yeah. So, I mean, that's one of those really big open questions people have is, if we could go back, could we manipulate the past to change the future? Now, of course, because we can't actually build a time machine, all of this are thought experiments and hand-waving more than rigorous science, but people have thought of different possible things that could happen that would allow you to time travel, such that if you went back and changed the past, then the future that would unfold, while it would be different, would be effectively a different universe to the one that you experienced before you traveled in time. So, there are lots of potential outs, but nothing's, because we can't test it, it's all more hand-waving than actual rigorous science.
Sure. It's I was keeping an eye on that whole Back to the Future movie. I'm sure you've seen it probably posted online, but how much of that stuff was actually came to be, and the Cubs, I guess, it just got knocked out of the world or the baseball playoffs there. So I guess that's not going to happen. No. So, okay. So, we'll tackle a couple, maybe a couple more conspiracy type theories here. Let's see here. We got, okay. So it's asked how we got to the moon. How did we get to the moon? What the big question is, how did we get through the radiation belt? There's a certain faction of people out there who claim that there's absolutely no way we'd ever get through that belt without, frying ourselves. And I personally don't believe that. I believe we did go to the moon. Now, everything else after that, what we did there or what we found, that's a whole nother ball game. But I believe we went there.
Yeah, so the radiation belts around the Earth, so these, of course, are the famous Van Allen radiation belts. And what they are is you have the Earth's magnetic field generated by the core of the Earth, and particles from the sun stream towards the Earth, and they get caught up in the magnetic field. Some get funneled into the poles, and so you see aurora. Others, of course, sit around in what's known as the Van Allen radiation belts. Now, the key point here, again, is that those belts were discovered by scientists, and those belts were very well understood by scientists. And if you actually read there's a number of really good books on, how Apollo got to the moon, etc. It was realized, of course, that those belts are there, and what they would have to do is you would calculate what's an acceptable dose. How much of a dose would you accept that an astronaut could take? And that would allow you to calculate how long you could spend in the belts. And what they did is basically they did what any sensible person would do, is they try to spend as little time in the belts as possible. And the belts of radiation, while they are energetic, we know how much of a radiation dose causes cancer or increases a risk of this, that, etc. So you can actually do the calculation, and you can calculate how dangerous it was to go through the belts. And if you go through quickly, it's the same as, we know how much radiation we get when we fly in an aircraft, and we could calculate how many aircraft flights we would need to do before it becomes a dangerous hazard to our health. And we know that it's quite a long time. We can weigh up those risks. So, I again, having looked at the Apollo plans, it seems like a very sensible thing is you spend as little time in the radiation belts as possible, but it's not a death sentence to go into the radiation belts. I can tell you a side story if you're interested.
Oh, yes, please.
Yeah. So what I mentioned previously is that the satellites of the Earth, the things that's dangerous to them are the solar flares, right? So solar wind, solar storms, they're the things that boost the background radiation. So that they're the source of the radiation. If you get a flare, you get a lot more protons and electrons, etc., flying through the Earth's atmosphere. Flying through space. The Earth's atmosphere tends to be protected by the magnetic field. So the dangerous thing to the astronauts was not the Van Allen radiation belts, but solar flares. And this was at a time when monitoring the solar wind, well, it's monitored in a lot of detail these days because people worry about satellites, wasn't as detailed as it is now. And if you look back over the records, it basically turns out that it was a fluke that all of the Apollo missions were in these windows when there was relatively low solar activity, And if they had been mistimed and the astronauts had been caught up there during a solar flare, a big solar flare, that would have been the dangerous thing, not the Van Allen radiation belts. So now if we were going to fly astronauts to the moon again, we would keep an eye on the solar surface and understand the solar weather, and we would put in place significant shielding to protect the astronauts if they are caught in a solar storm event. So, you know, I said it could have been a tragedy if they'd been caught in the open in a solar storm, but luckily it didn't happen that way.
Yeah, luckily. Okay. And so somebody writes and says NASA had already said that it's too dangerous to pass through this belt. I don't know. I haven't seen that. Depends where you seen it, where you found that.
Yeah.
I mean, I'm not arguing with anyone, but I'm just, you know, for me, I have no, you know, people don't want to give the human race any kind of credit. I mean, and you know, I strongly believe, you know, that we did get off this planet. I mean, these are the same people, though, and I'm not picking on Tomato Picker in the chat. I'm just saying that there are a group of people who will say that we're being visited by ETs, but then they don't want to believe that we can leave the planet.
Yeah. So the thing that gets me about the moon issue and going to the moon, and I'm going to try and use my language very carefully here, because it's not that hard a thing to do, right? In all reality, it's not that hard a thing to do. I can see it well within the capabilities of smart minds, of scientists and engineers to do this. So I can't see why we would... why there would have been a particular lie that we went there, and the part that you know, the one that for me basically nails it is that never once have the Russians said that the Americans never went to the moon. If the Russians believe it, and you know, they've got their own astronauts in space, etc., and we're trying to do the same thing. If they didn't think that the Americans actually got there, they would have used it as a big propaganda piece. But
I agree with that totally. Yeah. I would guess that too. I mean, because they have threatened other things. Russia, they've threatened to release satellite photos of different things, you know, to expose. So I imagine that they would if they knew. Now I got another question here. Comes from our chat room. Michael, can you ask your guest about the magnetic field of the Earth? Is it in the process of flipping? And if so, how will it affect the planet?
So the Earth's magnetic field, of course, is generated by the core, and we know that the magnetic field changes direction and I cannot remember the time scale that it flips on, actually. So we know that it changes direction. So you can see this in the rocks in the Atlantic Ocean. So as fresh rocks in the Atlantic Ocean have been laid out as the seafloor spreads, the magnetic field changes direction. So the one thing I do not know, I must admit, is how long it takes to reverse direction. But what's going to happen, of course, is that what's probably going to happen is that the strength of the magnetic field is going to drop off and then get stronger again. And so there's likely to be an additional flux of the solar wind onto the surface of the Earth for some period when the magnetic field is changing. How dangerous is that? Well, again, I don't really know, but life has come through all of the previous flips from one side to the other. What we might have, you know, is that life will be robust to it, but maybe our electronics will get fried, and that, of course, will be a pretty big upheaval. But life has lived through the previous flips of the magnetic field.
Okay, I see. Well, we've got a break coming up here, so I'm going to take this break and then we'll come back and talk some more. I'll take questions from listeners. A couple ways you could give them to me in the chat room at latenightinthemidlands.com by private message. Questions for the guest only, not stories, please. If you got anything lengthy, please call in. That's the best way to do that. So hang on with us for list is solar flares. And I guess some of the listeners are asking, why do we get so lucky? How come these things are always happening on the other side of the sun and they're missing us, the big ones, and how come those aren't frying our satellites? How have we gotten so lucky?
Oh, well, we're not always lucky. So we have been hit by solar flares. We have lost satellites. We have lost power stations on the Earth that you boost up the magnetic field and transformers give out. The thing is one thing people forget is that the Earth is actually quite a small target, right? We're a small planet. We're 93 million miles away from the sun, and solar flares go off in various directions, and we actually are a small target. But that doesn't mean that we get missed all the time. We have been hit by solar flares, and I said it is. I mean, it's one of those things, that it's a real risk because insurance companies care, right? So the fact that they offer insurance for satellites means that they've weighed up the risks and see that there are real risks to technology from solar flares. So now we do get hit.
I see. Okay. And, well, we talked about this a little bit with the stars, but somebody had asked about Planet X again. So I guess they're asking if my guest had seen any proof for it, and if they were tuning in early in the show, they probably would have the answer to this. But go ahead again on Planet X. Is there anything out there, and would you have any reason to not tell us? Has anybody come and said, "Don't you dare tell them"?
Okay, so let's. There's a couple of different things there. So let's start again with where we are with modern astronomy. And of course, what we have now is that people are building bigger and bigger telescopes. And what's happening is that the smaller telescopes, the 6-foot and the 10-foot telescopes, they are being turned over to what's known as survey science. And they are basically watching the sky. And there are telescopes dedicated to looking for things moving and changing on the sky. Some of them are looking for distant supernova. Some of them are looking for asteroids, etc. But everything in those images are basically poured over night after night after night. And there's no evidence whatsoever of there being an additional sort of star anywhere in our nearest vicinity. And I said the faintest stars that we have are these little red dwarfs, and there is one of the nearest stars to the Earth, which is Proxima Centauri. That's a red dwarf, but we know that's 4 light years away, and we can see that one. Anything in the solar system would be bleedingly obvious to even amateur astronomers at some level. So we don't have anything there. Now, the question of us, basically being bought off and told not to say anything, I think that really misunderstands the makeup of both the amateur and the professional community of astronomers in the world. So I'm an astronomer. I am British by origin, but I am now an Australian, and I'm at a university in Australia. And I'm employed by that university to do teaching and research. So I'm not a government employee in any way or whatsoever. And there is no overarching leadership of astronomy as such, right? There's no upper level that tells us what we can do and what we can look at and what we can't look at. It's driven by individuals. So even if there was somebody who had power over a group of astronomers in a particular country, there is no international control of astronomers around the world, be they professional or amateur. And you could imagine that's clearly the case because China is one of the up-and-coming scientific countries on the planet. They have a huge number of astronomers there. Why they would be told the same party line about something with regards to what an American astronomer might be told is just, it doesn't make any sense. We're not told what to say and what to do. We just get on and do our science.
Okay, absolutely. All right. So JJ asks in our chat, can you ask the guest what is the truth about climate change? Is it the sun or CO2 gases causing weather changes?
So climate science is a complicated science, and I know about the debates going on in the US and around the world, etc. So I guess the question is it purely driven by the sun, or is it, is there a man-made component to that side of things as well? And I think I should start off by pointing out first, I'm not a climate scientist, but also I have a lot of respect for climate scientists, and climate scientists around the world are like astronomers. There is no party line. There is no overarching group that tells them what to do. And there are climate scientists in Europe, in North America, in South America, Australia, all around the world. The consensus, and when I say consensus, what I mean is not that people got together and agreed, but what the common theme throughout the literature is that the man-made activities must have contributed carbon dioxide into the atmosphere. All right, that's what burning coal does. That's what burning oil and gasoline does, is put carbon dioxide into the atmosphere. And we know what the effects of carbon dioxide in an atmosphere will do. And we only have to look at our neighboring planet Venus to see that, right? Venus has got a thick carbon dioxide atmosphere, and it has what's known as a runaway greenhouse effect. Its surface temperatures are hundreds of degrees because it retains the heat so well.
Okay.
And so I should mention that my origin is Welsh. I was born in Wales, and Wales is a coal mining country. And I know a lot about coal, but I do know one thing is that it's fossilized trees that are made of carbon, and that carbon dioxide is going into the atmosphere. And it has to be playing a role. I mean, it seems to me quite clear that it must play a role at some level. So I can't give a definitive answer because I'm not a climate scientist, but to me, it makes sense that we've put a lot of carbon dioxide into the atmosphere and it's going to have an effect.
I heard a guy last night on another show say that that scientists have now found ways to use this carbon from the atmosphere and actually use it for fuel or something like that, and that it's really not a bad thing now. And I don't know, they come up with all kinds of crazy stuff. Ira is with us. He is on our phone lines. Ira, welcome aboard.
Hello, gentlemen. So good to hear you tonight. This has definitely been a really interesting conversation. I love this type of topic.
Good to hear you too. You're a little crackly.
Oh, am I? Oh, shoot. It's probably my Skype. I'm sorry.
No, it's okay. Go ahead. We can hear you fine, though.
Okay. Well, I was just going to ask, what do you think about the fact that, like, they've been finding and announcing, admitting basically that they're discovering water, like, everywhere outside of Earth. So at first it was the moon, and we went and bombed the moon to try to find more water there. Water now being on Mars and, all the other planets. I think even Pluto, they're now saying has water as well, if I remember correctly. But anyways, what are your thoughts as far as this round of announcements that they keep doing now with water everywhere?
Well, I can start by noting that water is probably one of the most common molecules in the universe, right? It's made of course, hydrogen and oxygen, and oxygen is hydrogen is the most common element. Oxygen is also a very common element made inside stars. And so we know that there's lots of water, and we see large quantities of water in other galaxies. So the question, I think it would be more surprising if there weren't traces of water in the solar system, right? It's one of those molecules you'd expect to find everywhere. The question that interests people like NASA, etc., is the quantity of water that's available. So the moon was a bit of a surprise because the moon's surface, if you look at it and it gets scoured by the solar wind, it doesn't have a magnetic field. It is a place where you think it would be difficult for water to be retained, and we only find it hidden away in the crater, so it's still there. It's frozen water, etc., doesn't see sunlight. Mars probably had a lot of water, and the big question is how much of it remains. But the fact that we're starting to find it is not really a surprise. I guess the question is what is the quantity? How much is left? And if we went there, would it ever be a viable source? But we shouldn't be surprised that we're finding water throughout the solar system and the universe, because it's a very common molecule.
What do you think about the idea of it seems like years ago, I don't remember the scientist that was talking about this, but they were saying basically that the kind of limitation on the thoughts of there being any kind of life outside the Earth would be whether or not there was water there. And so since water hadn't really been discovered up until that point, the claim was there's no possibility of life being outside of this planet because here's where the only water is. And in your thoughts, maybe is this kind of leading up to the idea of opening up the doors to say, yes, there is definitely the possibility of life now because there is water everywhere?
The two sort of are related. The difference with the Earth is not that we have water, but we've got a conspicuous amount of water.
The abundance.
Yes, the very wet planets. If you took a planet like Mars, where there's now only trace water, I think we would struggle to say that any kind of life, if it depended on water, would start and thrive there. Maybe in the past, when Mars was wetter like the Earth, there would have been more chance for life. But I guess what we don't know is, are there planets out there in the universe that have conditions on the surface that allow you to have appreciable amounts of water, to have oceans and streams and ponds and puddles and the kind of place where you expect life to start. And this is why a lot of the focus on the searches for extrasolar planets are looking for those planets in Earth-like orbits with a rocky surface, etc., because they could have a watery surface. So we think, yes, and we think the two are tied. The fact that we're finding water on Mars points to something that maybe happened in the past, but I would say at the moment doesn't say that we would really have any sort of life on Mars. I think this big hoo-ha will come when we find watery worlds around other suns. And I think that's only a matter of time eventually before we start to see those.
I see. Ira, anything else?
That's really interesting. I like your thoughts with that. We actually had another question come in from the chat. I can go ahead and ask it if you want to.
Oh, great. I'm not rushing you off. Go ahead.
Okay. Well, Tommy was wondering, he said, can you ask the guest if he believes that life exists on other planets? Have you ever seen any kind of extraterrestrial craft or anything along those lines?
Okay, so there's two questions there, I guess. So life on other planets. Yes, I would... and being a scientist, I don't like the word believe, but my understanding of science and the conditions in the universe, I would say that it's quite likely that there is life out there around other stars. I think the majority of life in the universe is probably closer to pond scum than people, right? Earth spent an awful long time as just single cell organisms, right? Billions of years before complex life arose. I think much of the universe could be like that. But, I think there could be more complex life out there. Have I ever seen any evidence of extraterrestrial life? I haven't. I'm not saying I haven't seen a few things in the sky that I've gone, oh, I wonder what that is. But, I'm in a community of astronomers. We spend an awful lot of time staring at the sky, and none of the guys I know have ever seen anything they thought was a spaceship or an extraterrestrial, etc. So I know a lot of people spend all their time looking at the sky and really not seeing anything.
I like your little analogy there, more pond scum than people. I don't know, depending on the political party that you're looking at, maybe there's that as well. Well, thank you so much for being here tonight. I definitely have appreciated you being here and listening to the conversation so far. I'll let you guys go, but have a great night.
All right.
Thank you.
Thank you, Ira. I appreciate the call, my friend. And all right. Well, okay. So the next question I've got here, let's see. Your thoughts on warp drive. Somebody asked, could you please mention warp drive? Explain warp drive for us. Less tech suave. Folks, by the way, give me your name, where you are at, not your address or anything, but, city, state, something like that. And if you would, tell me how you're listening to us when you write in. Kind of make it worth my while. I enjoy it. So, all right. So warp drive. Is it possible?
Okay, so warp drives are a very interesting concept. So, as I mentioned, Einstein wrote down his general theory of relativity 100 years ago. And it's mathematically tricky, and that means it's hard to extract out of the mathematics exactly what kind of things it predicts. But in the early 1990s, there was a researcher working in my home country of Wales, actually, in Cardiff, and his name was Miguel Alcubierre. And he was working with Einstein's equations and showed that you can take space-time and you can bend it and twist it, and you can create effectively a warp drive. And what that means is that you can create a bubble of space-time that travels at any speed you want through the universe. And one way of looking at it, what it sort of does is it sort of compresses the space in front of you and expands the space behind, such that you can propel yourself at any speed. So that solution is completely consistent with Einstein's special theory of relativity. That's part of the general theory anyway. And so you might scratch your head and say, well, how can you travel at any speed if the special theory tells you that the speed of light is the ultimate speed? And what it turns out is that because you're bending space-time, you actually carry light with you. So if you were inside the bubble and you did a little experiment to measure how fast light is moving, you find that it's traveling at 186,000 miles per second, which is the speed of light. So you take the bubble with you, so you take the experiment with you, and to an outside observer, you're making that light travel faster than light. So that's all well and good. That's how the space drive, the warp drive actually would work. The big question is, can we build one? Now, one of the things that you find is that as I said, you've got to bend and twist space and time in a certain way. And to do that, space and time bend and stretch in response to the distribution of energy in it. So to create a warp drive, you need to have certain energy distributed in a certain way. And the big problem is that kind of energy that you need is what's known as a negative energy. And I know that probably sounds a little bit weird, but it's a very understandable concept in physics are these things called negative energies. And so even our vacuum of space has a negative energy. So if you want to think about negative energy, if you have a balloon and you've got outward pressure, that's a positive energy. But if you could imagine the balloon had a tension and was sucking inwards rather than pushing outwards, then that's a negative energy.
We just kicked the negative energy out of our chat room, as a matter of fact.
Oh.
But go ahead. I'm sorry.
Okay. So the problem is that at the moment we don't have any sort of physical material that we could call a negative energy material that we could bend and use to build warp drive. So again, we have a mathematical solution from Einstein's equations, but we don't know if that solution is physically realizable. And I like to say it's an engineering problem now. The scientists have done their job, but it might be that in the future when people have pushed the vision of gravity and quantum mechanics together, that it will make sense that we will be able to shape negative energy and therefore shape space-time and have a warp drive.
All right. Fantastic. Okay, so let's see here. We've got, all right, good. People are starting to give me names now. That makes it more personal, I guess. Sarah is in London. So are the Buffalo Bills this week, as a matter of fact. Is there a God, she asks. I mean, I would assume that she just wants your opinion on that. I don't take it as sarcasm of any kind, but I guess your take. I mean, is there this godly energy? Is there this God force out there?
I am a card-carrying atheist, I'm afraid. So it's not in my viewpoint of the universe that we need a God. We have the laws of science, and they seem to basically control what we see going on. So, but there are lots of people who have a personal God, and if it helps them sleep at night, all the good for them.
Oh, that's right. Exactly. Just like a baby. You give them a pacifier, and if it helps them sleep at night, some parents say, well, at least I'll get a good night's sleep, right?
Yeah, yeah.
All right. So, David is in Texas. Now, he's asking about aliens. What do you feel? And I know Ira had brought that up, but what do you feel the probability is that there could be a race out there, I guess millions, maybe just a couple 100,000 even years advanced from us, and they're visiting us, or maybe they're somewhere in our solar system and nobody's found them yet? I mean, you look at kind of Pluto, they didn't expect to find a blue sky, I bet. So, you know?
Well, yeah, yes and no. I mean, so yes, the sky of Pluto was surprising, but it wasn't, earth-shatteringly surprising. We knew that there would be an atmosphere. We knew that it must have some materials in there. Whether it was blue or not, yes, that's a bit of an eye-opener. The chances. The question I would have is why a particular alien being, if there was an alien being, why they would come to Earth in the first place. What about this planet is interesting to them? If they can travel through the entire Milky Way galaxy, they've got 400 billion stars to choose from. Our sun is just a relatively boring G2 dwarf star. What would bring them to the solar system? So I said, well, I think there's probably intelligent life out there in the universe. I don't see why they would find the Earth interesting.
Maybe they see how horrible we are here, and they're thinking, uh-oh, they're figuring out how to get out here, and so we better keep an eye on them. Maybe.
But what are we going to do? I mean, we're stuck on the surface of this planet. We're basically dismantling all the possible ways of getting off the surface. We talk about going to other planets, etc. The furthest we have been is the moon, which, astronomically speaking, is next to nothing, and we've essentially forgotten how to do that. What would they be worried about, even if we are horrible to one another?
Yeah, well, okay. You may be right. Yeah, if my neighbors are horrible, I move out of the neighborhood. But
yeah.
So, go ahead.
Oh no, I'm saying that I said it. So probability-wise, I would say that it's a very low probability that we've had alien visitors. And again, we see very little evidence when we observe the Milky Way galaxy that there's a spacefaring species traveling between the planets. If they are, they're hiding their trails very, very well at all kinds of wavelengths. We don't see signatures that we think would be spacecraft traveling around. So it's a low probability that they've been here.
Okay, and so now I know a lot of UFO sightings can be explained. A ton of them can. But then there's those few that can't. And I mean, in your mind, do you expect to one day find that, we have been visited or we will be visited? I mean, or do you just, have you totally shut the door on that?
Well, look, I'm a scientist. Right. So a scientist always has to have an open mind, but your open mind has to be weighed by probabilities. And so if somebody tells me they see something that they don't understand in the sky, then you can trundle through your list of things, but you've got to weight them by probability, right? So is it somebody who's not used to the sky and they saw the planet Venus? And it is astounding how many people do not recognize our nearest planet on the sky and think it's a UFO. But as you go down the list, there are plenty of other things that go on the surface of this Earth to explain things going on in the sky, right? The military can have flights, etc. They'll never admit to them, and you go a long way down the list until you come to the conclusion that there's nothing left on your list that it must be aliens. To me, normally there are very Earth-based solutions to things that we see, or at least solar system-based solutions to the things that we see on the sky.
All right, great. And I'm going to give you one more here before we take our next break here. We got Josh. He's in North Carolina, and he says, will it ever be possible to travel through a black hole?
Well, that again is a good question, because we honestly don't know. We don't have a black hole that we can play with. So we're left in a similar situation to the warp drive, in that we have the mathematics that describe a black hole. So we know that in terms of Einstein's description what a black hole is and how it behaves. And if you have a spinning black hole, then at the center, the distortion is different to it when you have a non-spinning black hole. And it's thought that when you have that particular configuration, that if you fall into the black hole, instead of being just completely crushed at the center, which is what looks like it would happen if you fall into a stationary black hole, that you will be able to travel through the center, and that center would have to be connected somewhere. And there's speculation, and I should point out it's very much speculation, that somewhere might be either another part of this universe or part of another universe. So there are plenty of scientists thinking about it, but we don't have a black hole to play with, and you'd have to be actually a very brave test dummy to be dropped into a black hole and see what's in the center, right?
Very brave or very stupid, because you're not going to be able to tell anybody what's there, I have a feeling.
Absolutely. I said at some level, so I said that science comes with a bit of a range of, credence at some level, and how much is speculation and how much is hard science. They're traveling through the center of the black hole. That's more hand-wavy than a lot of robust science.
All right, great. Well, hang on with us again here, Grant, and Grant, we are back, and I've got more questions here from our listeners, and I will give you, before we're done, I'll give you an opportunity to get out anything that you'd like as well. So Sherry is in Vermont, and another, I think, pretty good question. How do you know that dark matter actually exists? I guess that should be how do they know? How do you know? How does anybody know?
Okay, so I should point out that a lot of my job actually is looking at the effects of dark matter in the universe. So there's a couple of key things here. So firstly, let's talk about it from an observational point of view. So when astronomers look out into the universe and they measure the velocities of stars and the positions of galaxies, etc., and we try to explain those within the laws of physics as we know them. So we've got our pictures of gravity, etc. Then we find that it doesn't work. So if we look at how fast the sun is moving around the center of the Milky Way galaxy, it's moving at around 220 kilometers per second. And if we add up all of the stars there are and ask what their gravitational pull is on the sun, there's not enough gravitational pull there to keep it in its orbit. So the sun should just fly off out of the Milky Way galaxy and into deep space. So these observations basically led people to conclude that something else is holding the sun in its orbit. And it's not just the sun, it's everywhere we look, we see similar kind of things. And it was proposed first actually back in the 1930s, but then evidence grew through the 1950s, 60s, and particularly 70s, that essentially to describe what's going on in the universe, we need more gravity than can be accounted from the stars and the gas that we see. And it was proposed that there was matter there, dark matter, which is matter that doesn't emit any light, but provides the extra gravity that holds things like the sun in its orbit. So when I write a paper now on some of my most recent observations, looking at the destruction of the Powell 5 globular cluster, etc., I will talk about how much extra gravity is needed to explain my observations in terms of this dark matter, how much dark matter there would need to be. So the question then is, of course, what is dark matter?
That was the next question too. Yeah, so go ahead.
Right. So observationally, we need this extra gravity. We have this stuff called dark matter. What is dark matter? So there are several possibilities. One possibility is that dark matter really is a material substance that is dark. And the question we have is there anything in the universe that could have those kind of properties? And within particle physics, there's plenty of room for heavy particles, things that aren't like the electrons and protons and neutrons that we know, but particles that don't interact electromagnetically, so they don't emit any light. So there's plenty of room for those. So a lot of people have come down on the side that dark matter could be a physical substance, and if it is, it's probably going to be a particle, like one of the unknown particles that are possibly out there. We've ruled out lots of things that dark matter isn't. We know that dark matter isn't things like dead stars, because dead stars glow in the infrared, and we've scanned the skies in the infrared and we can't see them. We know that dark matter isn't black holes, because black holes have what's known as a gravitational lensing effect on distant objects, and we've looked for that and we can't see it. So we've ruled out a lot of things that dark matter isn't, and particle physics is where people think the answer is. Now, within science, there's not 100% agreement that is what dark matter is. And there's a group of people who say that that dark matter is effectively a manifestation of our lack of understanding of gravity, that there's something actually wrong with our gravitational equations, and we need to look on that side of things rather than the particle side of things. Now, this is the way that science works. We have a question, and people are proposing different answers, and people are searching for those answers in different ways. So the people who think that it's the particle side of things are building particle detectors to look for potential dark matter signatures. So this is one of the things that they're looking for in CERN, is that are there any particles produced that could be dark matter?
All right.
On the flip side, there are people who suggest that it's a modification of gravity and ask the question, well, what's the observational consequences of this modification of gravity? At the moment, we don't have a definitive answer. So nobody can tell you exactly what dark matter is, but something is needed to explain how the universe behaves as we observe it.
All right. And Tom, he is, I think that's San Francisco. He asks, is dark matter the same as dark energy? And if not, what is that?
Okay, so in the simplest picture, no, dark matter is not the same as dark energy. So we have to go back a decade or so now to when people were observing the distant universe and measuring the expansion of the universe, which is something that we do regularly. They noticed that with the detailed observations, they were seeing that the expansion is starting to accelerate. And if you have to ask yourself, what do you need in the universe to get an accelerated expansion of the universe? You need a dark energy term, as we call it. So this is something that goes into the equations of relativity that gives you accelerated expansion. Now, matter doesn't do that. Matter acts as a brake. Matter slows down expansion. So we know that dark energy cannot be matter-like. It has to be something distinct and different. There are now ideas coming that the two are related, that maybe dark energy and dark matter can sort of change form. One can change into the other. And this is what new sets of observations are going to try and find out, is if they are related. We know that they are distinctly different things, but they might interact somehow.
All right, great. I hope that answers your question. And we got, it just says Frey, F-R-A, so I guess that's Frey in the UK, and it rhymes. What is a black hole? What I mean is, what is it like inside of a black hole? I mean, do we really know? I know I don't know, but do you know?
Well, again, we don't have a black hole, right? So we don't have something that we can actually play with. But again, given the equations of relativity, we can work out what would happen if you cross that boundary into a black hole. Let's imagine that you've got a black hole that has just been sitting there away from everything else, and you fell in. Well, it would just be more empty space, right? There would be nothing in there except for empty space. And as you fell, you'd feel the gravitational field get stronger and stronger and stronger, and you'd get torn apart. Now, most black holes, though, are in the vicinity of other matter, right? So you have a black hole, and there will be matter spinning around it. Some of it will be falling in all the time. If you fall in, then what you would see is a very energetic environment, as basically you've got very high-speed rain of material all around you. So it wouldn't be very pleasant. It's not going to be very pleasant anyway. It would just make a bad day even worse by having additional material swirling around inside the black hole.
Okay, fascinating. It is. It really is. All right, we've got listening in something. I don't know. I don't know what that is. They abbreviated it. I have no idea. But okay, SA, whatever that is. Probably another country. If gravity is the weakest of the four forces of nature, and we can observe black holes, is it plausible that the other three forces of nature can result in their own variation of a black hole?
It would be very difficult. It would be very, very difficult to make a black hole out of the other forces, partly because they are so strong. So one of the things we have with gravity is, unlike electric charge, which comes in a positive and a negative type, mass is all positive. So, all mass is positive. So you pile in mass and the gravitational field gets very, very, very strong very, very quickly. If you try to do that with, say, negative charges, if you had electrons and you started to pile in electrons, the electric field that would produce would start to pull positive charges in, and they would neutralize the effect of the negative charges. So because mass only comes in this positive kind, you can't sort of neutralize it in the way you can neutralize the other forces. So you can only get black holes when you can build up sufficient quantities of mass in a particular place.
All right. And we got Tyler, and Tyler is in Jersey. And, boy, some really good questions here tonight. In E equals MC2, how does the speed of light influence the conversion of matter into energy? What property of light would cause this?
Okay, so E equals mc squared, that comes from Einstein's special theory of relativity. So the question is, why is the speed of light in that equation? So in reality, that c is not the speed of light. It's the characteristic speed which you have inside Einstein's theory. It's the speed at which a massless particle will travel. And it turns out that light in our universe is a massless particle, and therefore it travels at that speed. So we call it the speed of light, but it's sort of like the fundamental speed of the universe, and we just happen to have particles in the universe with no mass that travel at that speed. So we use the terms interchangeably. Why does it come in? Because that fundamental speed is the thing that allows you to transform between things going on in space and things going on in time. And in special relativity, the two things are connected. And so you need some sort of conversion between the two, and it's that speed. And because that enters into the equations, because you can mess around with space and time, it ends up in that E equals mc squared equation. So it's not actually a property of light that does that to give you the conversion factor. It's the conversion between time and space that does that.
All right, fantastic, and the questions keep coming in, so I'll keep giving them to you. We'll try to get them all in here. A tomato picker says, Dr. Mehran Tvolky, an Iranian plasma physicist and nuclear scientist, has already stated that a second sun is now noticeable on the horizon, which will reach us in 20 to 30 years. What are his thoughts?
Based on what evidence does he say that there's another sun on the horizon? I mean,
I would have no idea.
yeah. So I mean, it's fine. I can say all kinds of things. I can say that I've got unicorns at the bottom of my garden, but until I see the evidence that somebody makes these claims with, I mean, that's the whole point of science, right? You don't take somebody's claim without taking their evidence. And if somebody says to me that there's a star on the edge of the solar system or whatever, I want to know their evidence. And often you find these stories that people will make these claims and that there is no evidence behind it. If there is evidence, I'd be happy to take a look at it, but there's nothing in all of the data and papers that I've read that there's any evidence of there being a second sun in our solar system.
Yeah, well, and again, if folks, if you've got evidence, and I'm not talking about, a lot of times what people will do is they'll send me a picture and they'll say, hey, here's a picture, and I'll be like, oh, great, did you take it? Well, no. Well, who did? Well, I don't know. I found it on YouTube or I found it on here. It's like, well, we've got to know who took the picture, and we've got to know things. We've got to make sure that they actually took this picture, and we got to rule out lens flares. We got to rule out a lot of things, and so a lot of people don't take the time to do that. And let's face it, if you put it out there that we're all going to die tomorrow, it will get a lot of hits. I mean, it just will. And I'm not saying that none of it's, could wind up being true. I'm just saying I'm the same way. I like to see solid evidence. I've had one researcher, which it doesn't bother me anymore. I mean, it is what it is. But I had one so-called researcher who I asked a question, been on my show a ton of times. Always gave him free reign. And then I asked him, I found a flaw in one of his pictures, and boy, he was not happy. He cursed me out. So, so if I get anything credible that passes my credibility, I'll share it with you. You tell me what you think, because I think you'd probably be one of the guys to ask, right?
Absolutely. As I said, science is all about evidence. It's not about proclamations, it's evidence. And you don't take anybody in their word, you take them on their evidence.
So if you were looking, let's go into this for just a second. If you were looking for an object like that, you personally, I mean, you look into the stars. I mean, you would be able to find it if it was there.
Absolutely. I said we have, and in fact, it's growing the number of surveys that go back and they look at the same patch of sky over and over again, looking for things that change. I mean, the Meteor Watch people do this over huge swathes of sky, right? Looking for faint rocks that move in the solar system. You would notice a star. It would be very obvious. I've almost slipped into a British slang there, but I won't. But it would be very, very obvious if there was something like that in any of these images. And as I mentioned to you before, it's not just like observatories in the US, but in Europe and in China, in Japan, in Australia. Everybody's doing these monitoring programs for different reasons. And the thing is if the astronomical community thought that there was a second star to study in the solar system, they'd be over it like a rash, right? It would be like the hottest topic in town. But nobody's talking about it because it's not there.
Yeah, well, and I'm with you. I mean, I'd like to see evidence, and if there was a period of time when people were just getting upset, the Planet X people were getting upset with me because they kept throwing stuff at me, and I mean, it's like I'm not gonna go along to get along. If I find a flaw, I'm gonna say I did it. Look, I've got no horse in the race, really. I mean, if it is coming, I'm dead anyways. I mean, we all are pretty much. I mean, we're not going to choose who lives and dies. That thing would. So, and if it's not, well, then, I've not lost any sleep for something I don't need to worry about. So,
absolutely.
That's the way I see it. All right. So we got Hens, and he is in Japan. How do we know the age of the universe? Is it really possible?
Yes, through a lot of detective work. So, age in the universe has been one of those problems that we have been looking at now for a very long time. And we started by aging stars and asking the questions like, how long would it take a star to turn so many amounts of hydrogen into helium and all this kind of stuff. So laws of physics, etc., are very important. In my own field of cosmology, we have particular equations that tell us how the universe has expanded over time. So it tells us that the universe has expanded at a certain speed, and what we can do is we can measure the speed of the universe today, this thing known as Hubble's constant, and we can look at the other properties of the universe, and we can tie that into the universal history, and that gives us the age of the universe. So it's actually complicated is not the right word. There's a level of detective work there, finding out the bits and pieces that plug in that give us the age. It's like, if you have a horse and you count the teeth and all that kind of thing, that's what we're doing for the universe. We're getting all those bits and pieces, and that gives us the age.
Yeah, okay. All right, great. So we have a few more here, and after that, if there's no calls or anything, then we'll break. So Joe and Fran, and they are in Niagara Falls, Canada. That's wonderful. I haven't been to Niagara Falls in a long time. We love your show so much. Can you ask your guests, and of course I had to put that in there because they wrote it, if our galaxy was on the edge of what we can currently see as the visible universe, would we be able to see 13.5 billion more light years further than we can at our current location? And if so, does that support the Big Bang Theory?
So, yes. So essentially, the visible universe is a sphere based around us from which we have received light since the birth of the universe. If we could instantaneously take ourselves to another galaxy which is on the edge of our observable universe, there would be a sphere around that galaxy which would be its observable universe, and it would look pretty much like our observable universe. Yes, that's exactly what we would expect from the Big Bang picture of the universe. So one of the common misconceptions about the Big Bang is that it was like an explosion into pre-existing space, such as like a hand grenade exploding, and that we are somehow debris flying off. But that's not actually what the mathematical picture of the Big Bang tells us. If we go by what our measurements of the universe are telling us today about the extent of the universe is infinite in extent. It travels infinitely far in all directions, and it was infinite in extent when it was born. So the Big Bang, the birth of the universe, took place in an infinite amount of space, and the universe has been cooling and expanding ever since. But at every point in the universe today, you would get a very similar view. So if we take that distant galaxy that we were sitting on and then jumped to the next one at the edge of its observable universe, we'd have the same view again. So that's precisely what we'd expect from the Big Bang picture.
All right. Patrick, not sure where Patrick is, but Florida. Patrick, one question, he's got 4 here. One, did Grant believe time travel is possible? You did say, mathematically, yes, it is possible. Right? Yes. Okay.
Absolutely.
And number 2 was also, what would happen to Earth if the Van Allen belt collapsed? So I don't know if you want to touch on that briefly.
Collapsed. Well, the only way the Van Allen belt would collapse is if you got rid of the magnetic field of the Earth. Which we know when we have a magnetic field reversal, it gets weaker and gets stronger again. But if it collapsed completely, then the solar wind would start hitting the Earth's atmosphere constantly, and that can have an effect of basically ablating some of the atmosphere, would get blown away. But also, and more dangerously, we would get this high energy radiation from the sun, the protons and the electrons hitting the Earth's surface. And those are the kind of things that crash through your DNA and can result in cancers. So it would have an effect. Our surface is protected by the magnetic field.
All right, and let's see here. He's got a couple more here. Did your guest see the movie Gravity? And if he did, does he feel an astronaut could have survived as Sandra Bullock's character did?
I saw the movie Gravity, and the great thing about science fiction is that it's fiction. I think it would be, space is a very dangerous environment, and for Sandra Bullock, she went through so many dangerous episodes to get back to the Earth. I don't think that the entire series of incidents that she went through would actually be survivable. It's such a dangerous place. You can't hop from one space station to the other space station and all this kind of thing. Bits of it are true, but not. You couldn't imagine the entire story taking place. I would like to note, though, I think astronauts are some of the bravest people on the planet. It's an exceedingly dangerous environment. Them and deep sea ocean divers.
Oh yeah, absolutely. I think I'd feel more comfortable with going to space than I would being in the deep sea.
I think I'm with you. I find the deep sea rather scary and off-putting.
Yeah, absolutely. There's things that we've proven that there's life there and that it will eat you.
Yes.
All right. Last question here from Patrick is, what does he think of how close the close to nearing Halloween asteroid got to Earth before it was noticed? So I don't know if you've actually had a chance to look into this asteroid, if you heard about it.
I haven't, but I said these stories come along quite regularly. Let me just see. I'm going to do a quick Google here as I'm talking to you.
Okay.
Spooky. So it's 1,300 feet. So that's actually a reasonably big piece of rock. But how close is it coming? 1,500. Okay. So this rock is traveling at 22 miles per second, but it is 300,000 miles from Earth. So it's further away than the moon. So we, that's the kind of rock that we want to find, and that's the kind of rock that we look through the solar system to find, because it could be dangerous if it hit the Earth. So the fact that they found it quite recently probably suggests that it's on an orbit that was pointing relatively straight towards us. So it didn't move a lot across the sky. Those are the hard ones. Those are the ones that they've always got their eyes open for. But it's not surprising that they find these guys. They're going to keep finding more and more of them, actually.
We ought to start mounting cameras on these things, of course, without changing their direction. But if they're especially if they're going out into deep space, I mean, you don't need no fuel. There are lots of ideas about hopping onto asteroids or mining asteroids, because there's lots of asteroids are made of iron and rare elements and all this kind of stuff. So there's been talk about getting up there and actually mining these things. So I'm looking forward to it. Actually, I think it'll be quite exciting. Absolutely. All right. So I have just a couple more questions here from our listeners. We'll take Michael's question first. He's in New York City. How can, according to Newton's conservation of energy, antimatter and matter, when they interact, annihilate each other? Does the energy just transfer to another vessel, or is the matter and antimatter truly destroyed? I guess energy can't be destroyed, right? Can it?
No, it's not destroyed. So what happens is, there's two different things here, right? So you get two particles meeting, and they have mass, and that mass disappears. So mass is not conserved, but energy is. If you've got a proton and antiproton, they meet and they annihilate, they get turned into high energy radiation. So they become photons, they'll become gamma rays and X-rays. So when you see a nuclear explosion, and I don't want to see one from up close, but when you see a nuclear explosion, the first thing you see is the flash, right? Mm-hmm. That flash is that is matter having been turned into energy and being carried away as electromagnetic radiation. So the flash in a nuclear explosion is mass that has been converted to energy.
All right, great. And last but not least, we've got Marty. I wonder if it's the Marty from Back in the Back in the Future, or whatever it is there. Marty's in Columbia, South Carolina. Well, hello, neighbor. It says, how can, according to Newton's, I think this is the same, it looks like the same question. Oh, no. Okay, this is different. When they interact, do they, yeah, it is basically the same question. Yeah, they're asking still again if these energies annihilate themselves. So that would be, you just answered that, really. I mean, there's more to it, but it's basically the same thing. So
okay, yep.
So that does it. So what I'll do is give you the floor now to get out anything that you'd like, and I thank you so much for joining us tonight.
Anything that I like.
Yes.
I guess I haven't prepared for this side of things.
Well, if you have websites or anything like that you'd like to plug, or whatever, you've got appearances, other shows you're going to be on, I don't care. Go ahead.
Okay. Well, look, I am on Twitter at cosmic_horizons. And if there was any questions that people wanted to post to that, I'd be happy to. I can plug a book. I have a book coming out next year. And the title is not 100% sorted yet, but it's probably going to be A Fortunate Universe. And it's going to be around the question of fine-tuning in the universe. And this is this notion that if the laws of physics were slightly different, then the universe could have easily ended up as a very sterile and dead place. And examining the entire question of fine-tuning in the history of the universe. Other than that I think science is great. I think that's the most important thing.
All right. Well, listen, thank you so much for taking this time out to be with us. I do appreciate it, and enjoy the rest of your night and the rest of your week, and thank you. Until next time.
Thank you very much. Hope to talk to you again.
All right, absolutely. Have a great night, my friend.
Okay, bye-bye.
Bye-bye. All right, folks, there you have it. Geraint Lewis and good evening, Geraint Lewis. Welcome to Late Night in the Midlands. How are you?
I'm good, thank you. How are you?
I am doing just fine, and I want to welcome you to the show, and we are live. So thank you for being here.
No problem.
All right, great. Well, I thought maybe we'd start with a little bit of background and where your interest has led you in this field of astrophysics.
A bit of background. Okay, so I'm actually a professor of astrophysics at the University of Sydney, and my area of research is focused on mainly cosmology, studying the large-scale universe, gravitational lensing, and an area known as galactic cannibalism, when one galaxy eats another galaxy. So those are the key areas I work in, but I've also got a strong interest in lots of physics, actually, especially things like special and general theories of relativity.
I see. And what's your thoughts? I don't know if you've seen it, but I've seen an article where there's these two stars kind of merging as one. Do you know what I'm talking about? And what's your thoughts on it?
I'm not sure exactly which one. There's a lot of merging stars out there. There's especially very dense stars, neutron stars. They're the ones that they spiral together and they sort of eventually collide. So we see stellar mergers quite regularly. But do you remember what the key point of the one you saw was?
No, they said that it was a binary star system and that the two stars, their centers, looked as though they were combining to each other and was going to become one big star, they said, and then, of course, it would, turn into black holes because it would probably collapse on itself. Yeah. But I think they said it was the closest I can't remember offhand. I think it was they said it was a very close star system.
Okay.
And so they got a good look at it, and that's all I know really about it right now. So that's why I thought I'd ask you.
Yeah. I said there's a lot of. In fact, most stars in the universe appear to be in binary systems, but most of those stars are well separated. So one star doesn't really influence the other star, other than in its orbit. But we do see some stars that are close enough that effectively they're touching, and there's mass going from one to the other. And especially when you get these really dense little stars, these neutron stars, that's when their orbits basically lose energy very quickly, and then they collide together, and you get a violent collision, possibly black hole formation when that happens.
I see. So then, is there any evidence of anything like that? Not the two stars combined here in our solar system, but I might as well get it right off the table now because people will want to ask: is there any evidence of a second star, a dark star, or anything like that out in or around our solar system?
You mean as in orbiting our sun?
Well, it could be. I mean, anything like that. I mean, so I hear that, people say, well, there's a dark sun out there somewhere in our solar system that, our sun has to have a companion somewhere.
Not that we can see. I mean, the thing that's happened in the last sort of 20, 30 years, which has changed astronomy, is that people have surveyed the sky to great depths and at many wavelengths. And if there was anything remotely like another star anywhere near our solar system, we would have seen it, and we would have also detected its gravitational influences. So our sun does appear to be just a lone star. There doesn't appear to be another star anywhere remotely close to it. Wow. I mean, the smallest, dimmest stars we know are red dwarfs, but we would easily see a red dwarf star anywhere close to us.
We would. So, because I have people who tell me that, well, it's not coming across the solar system. It's coming from below, or it's coming, they tell me that I wouldn't be able to see it until, it was too late.
No. So astronomers love those areas above and below the solar system, right? Because, the planets are out of the way. So we look in those areas all the time, and there's not another star hidden there.
All right. And if there was something, this is something that I've brought up before with all the amateur astronomers and there's always somebody out there who would love to be that whistleblower. And so that's why it's kind of hard, for me. I've always been on the middle of the fence with it. Like, I don't know. Maybe there is something out there, but, I know there's a lot of baloney about it. So I thought I'd bring it up. Yeah, so we don't have nothing. Oh, what about this asteroid that's supposed to be coming close to the planet on Halloween now? Do you know anything about that?
Oh, there's probably a lot of them that's come close to the Earth's orbit around this time. I mean, there's a lot of bits of rock in the solar system. I mean, again, from looking at the sky, we see that the solar system is filled with rocks of various sizes, and lots of them come across the Earth's orbit. But for all the ones that we've detected, and we're now trying to get down to the smaller ones, we know that the chances of any of the bigger ones hitting the Earth are next to nothing for. I'm not sure how long the time frame for it, but it's many decades into the future. We can be pretty sure that we're not going to be hit by anything reasonably big. There are still lots of relatively small rocks, of the hundreds of feet or smaller size, which will hit the atmosphere. These things hit quite regularly. So we will have continuous bombardment of meteors and meteorites, etc., but none of the big stuff is coming close to us.
Okay, and so then it was probably just a freak thing, I guess, with Russia then, because, I found it kind of strange that we had an asteroid, as you know, that
was a new description of gravity. And that sort of encompasses already what Newton had told us, plus there's extra information. And one of those extra things that's in there is that gravity is related to space and time. So you've got this concept of space-time, and that gravity is the distortion of space-time. So you have a massive object, it distorts space-time, and that distortion is the gravity that we feel. So that particular theory of gravity is exceptionally powerful in that it describes things very, very accurately. It describes the motions of the planets very, very well. So you've got Mercury's orbit, which was always found to be slightly discrepant with Newton's description. But when you use Einstein's general theory of relativity, you actually get the orbit extremely accurately. So that's what we now know as gravity. We talk about gravity in terms of Einstein's general theory. Now we know that that general theory of relativity can't be complete because there's a tension in modern science, and that tension is between Einstein's description of gravity, which talks about the universe on the large scale, and quantum mechanics, which talks about the universe on the small scale. And when we want to try and use those two descriptions of the universe together, we find that they don't really work together. And this is why people feel that there's got to be a next step up in terms of of how we understand the universe, which combines quantum mechanics and gravity together into this one framework. So we have a really good description of gravity. We know it's not 100% correct, and people are working on trying to get this unified picture. So the question you have about why people don't feel the motion of the planets is, I think you have to turn the question around and ask yourself why you would expect to feel the motion of the planets. So if you are in your car and you're trundling along the highway at, trying to remember, it's 55 miles an hour is your typical speed in the US?
Yes, sir.
You don't feel the motion, right? I mean, you feel the shaking of the car, and you can hear the wind blowing over the car, etc. But your body doesn't sense that motion. In fact, your body can't sense motion. So if I took your car and I put it into space, and so that you're not rumbling along the road and there's no wind blowing across the car, and I give you a big push and then off you go sailing through space, you would not feel that motion. We don't feel motion. What our body feels is acceleration. Our body is an acceleration detector. So when you hit the gas, you feel that acceleration because the car pushes against you. And when you slam on the brake, you feel the deceleration. But actual motion, you don't feel.
That day or around that time that was passing close to Earth, and NASA had said that, we had nothing to worry about, which, so a lot of us didn't. But, that comet, I think, came, because of it, and hit Russia. But they say, no, it wasn't connected. I mean, could it have been?
Well, they would be very different sizes. I mean, I know the rock that exploded above Russia looked very spectacular. And, explosion-wise, it was a big explosion, but very high up in the atmosphere. But the actual rock that did that was probably quite small, of the tens of feet size. The rock that NASA would have been monitoring would have been something much larger, probably the hundreds of feet sort of diameter. Those ones are ones which could do substantial damage if they hit the Earth. Could they have been associated? Possibly. I mean, the rocks are not just often lone rocks. You get one or two of them traveling together, and this might have been a small piece following the big piece. But there are lots of astronomers at the moment now who are looking at that dash cam footage, looking at the entry trajectory of the rock, and trying to trace the orbit back to see where that rock came from. Nice. But we probably get hit by rocks, of order that's tens of feet quite regularly. It's just that most of them will be over the ocean, it's only now we get into the time where everybody has a camera on them, right? So they can photograph these things. So they're not that rare.
A little rock, as you called it, like that, and the havoc it caused in Russia, I couldn't imagine something big. I mean, what would it take to affect the entire globe? I mean, I hear that, like rocks like what hit Russia, it's kind of isolated. And so I guess whatever they think took out the dinosaurs had to have been really, really big, right?
Yes. So that's when you're getting up to kilometer size And there are, we know there are chunks of rock kilometer size and bigger in the solar system. So the big thing that's happened about the Russian one is that it exploded in the atmosphere. So it was a big explosion, but it was high up. The dangerous ones are the rocks that can get down low into the atmosphere and explode close to or on the ground, and they're the ones that can have damage over a very, very large area. But those are the ones that we're trying to track. That's why there's a whole range of telescopes around the Earth now which are being set up to monitor and search for these rocks of 100 feet plus and try to monitor them and work out their orbits for the future.
I see, and I'm sure they try to monitor other planets that get hit. I know a long time ago one was going for Jupiter, but Jupiter, I mean, we didn't see much except for a flash. I guess it'd be nice, as long as it's not this planet, to watch something like that.
But yeah, so for Jupiter, it was hit by Schumacher-Levy 9 back in, I think it was 91. It was quite a while ago now. And you have to remember that Jupiter is a very different planet to the Earth, right? It's gas and then liquid, and then maybe in the middle there's some rock. So there's no surface to hit. So the thing when it actually goes through the atmosphere and explodes in the atmosphere, similar to what happened above Russia, the energy gets dissipated into the gas. And so there were scars on the clouds of Jupiter. I mean, and those scars were much bigger than the Earth. But eventually the clouds basically mixed it all away and it disappeared. But, there was a very large amount of energy was deposited into Jupiter's atmosphere from that. Yes, we don't want it to happen to the Earth.
Yeah. All right. So now I've had guests come on and kind of I've had a couple lately who disagree on the aspect of gravity. And I've had some tell me gravity pulls, others say it pushes. And I thought maybe you could explain gravity just a little bit for us and why we do not detect the movement of the planet, etc. Because there's also, in another part of this, there's those who are trying to convince everybody that the world is flat. And still, I believe it or not. And so I thought maybe you can get in a little bit about gravity and why we don't feel the movement of the planet.
Okay, so where to begin? I think the best place to start is with Isaac Newton, right? So this is now back in the 1600s. And what Isaac Newton did for us is he gave us a mathematical description of how gravity works. So high school children learn this now. They write down Newton's laws of motion, Newton's laws of gravity, etc. And what Newton told us is that if you have massive objects, then the amount of gravitational pull you get depends upon how much mass you have there. And it depends also on the distance apart, or the square of the distance apart. And it's an exceedingly powerful mathematical law. So so Newton was able to calculate how fast an apple falls, and using the same equation could calculate how long it takes the moon to go around the Earth. And it's the same mathematical framework we use today if we want to put a rocket into space or the New Horizons flying to Pluto. They used Newton's law of gravity. Now, what Newton's law of gravity doesn't have in there is an explanation for what gravity is, right? It's just a law that tells you that this is how much force you get. And to describe gravity in the modern context, what we use is Einstein's general theory of relativity. So this theory is 100 years old this year, and Einstein basically wrote down his famous set of equations, which